Hello everyone, welcome back to my channel Fine Math. And in this video what we are going to do is that we are going to do an example of on gradient and directional derivatives that we have discussed in lecture 1. So please, if you haven't watched lecture 1, please go and watch lecture 1 because you won't understand what we are talking about in this video if you haven't watched that particular lecture. So let's dig right into it. So you can see the question on my screen. So the question is, find the gradient of a function f of xy which is x square y. So the function is given as x square y plus y square x, and we have to figure out the gradient at point P given by 1 comma minus 1, that is x is equal to 1, x is equal to 1 and y equals to minus 1. Then we have to find the directional derivative in the direction u, which is I minus j cap. Okay, so let's find the gradient first. So gradient f of xy, the definition is ex, or let me use I comma. So here I have used I cap and j cap, so let me use I cap and j cap as my unit vectors. This is the definition of the gradient, right? So let's plug in our function. X comma y is equal to I dx. Here we have x square y plus y square x j df by dy. Our function is x square y plus y square x, right? Now this x derivative will only act on x, it won't act on y. So therefore we have let me do one step to make sure it's clear. So the reason why y comes out, because it doesn't act on y, right? Plus y square d over dx x plus j, and this would act only on y, right? The y derivative. So x square comes out, you have d by dy del by del y plus x del by del y of y square. So let's take those derivatives, and you have y 2x plus y square, and derivative of x is just 1 plus j cap. We have x square, and the derivative of y is just 1. Similarly, the derivative of y square is 2y. So finally we have a gradient f of x comma y, which is I 2xy plus y square plus j cap x square plus 2xy, right? So let me box this, right? Okay, so now we are asked to find the gradient at a point P 1 comma minus 1, right? So let's just plug this in. Gradient of function x comma y at P 1 comma minus 1 is gradient of f at 1 comma minus 1, right? Which is equal to gradient of f 1 comma minus 1 is equal to I 2. In place of x we have 1, in place of y we have minus 1. So let me write at 1 comma minus 1 plus y square, which is minus 1 square, plus j cap. X square is 1 square plus 2, x is 1, y is minus 1, right? Gradient f of 1 comma minus 1 is equal to I, this is minus 2 plus 1 plus j 1 minus 2, right? Okay, let's continue. 1 comma minus 1 is minus I cap minus j cap. Is it clear? Okay, so that's why, so we have found out our gradient at the desired point, which is 1 comma minus 1, right? So this is our gradient. So the our first problem is solved. The second task was to find the directional derivative. Directional derivative in u direction, which was given as I minus j, right? So the definition of directional derivative, and remember what directional derivative means, right? I told you in lecture 1 that directional derivative is nothing but the rate of change of function in a particular direction, because in 2 dimension you have a lot of directions to approach a particular point, because the domain is xy plane, and you want to reach at a particular point, in this case 1 comma minus 1. So there are a lot of infinite directions in the xy plane through which you can actually approach this 1 comma minus 1. So the directional derivative is an approach in which you restrict yourself in just one direction, and you ask the question that what is my rate of change of function if I move along this direction. So that's what directional derivative means. And directional derivative d in the direction u cap. So u cap is a unit vector of my function f at a particular point x0 y0 is nothing but gradient of my function at x0 y0 dotted with unit vector, right? So in our case x0 is 1, y0 is minus 1, right? And our u vector is given as I cap minus j cap. So u cap, which is a unit vector, which will be I cap minus j cap divided by the modulus of u cap, which is I minus j. Modulus is just 1 square plus minus 1 square, right? Which is I minus j, square root of that, which is root 2. So our unit vector is 1 over root 2 I cap minus 1 over root 2 j cap, right? Let's just plug this in this equation, and we have directional derivative in the direction of u cap of my function at particular point x comma 1 comma minus 1 is equal to the gradient of my function at 1 comma minus 1 dotted with u cap. So we already found the gradient. Gradient was this guy, minus I minus j, and we have the unit vector, which is 1 over root 2 I cap minus 1 over root 2 j cap. So when you multiply this, when you take the dot product, you have minus 1 by root 2 I cap dot I cap minus becomes plus, and then you have 1 by root 2 j cap dot j cap, right? So you have 1 over root 2 minus plus 1 by root 2, which is actually equal to 0. So therefore my gradient vector, my directional derivative in the direction of u cap is actually 0. So what does that mean? What does it mean when it comes to 0? It means that if you move along this direction at this particular point, your function does not change. So therefore your function has a either maxima or minima at this particular point, right? Because your directional derivative is 0. It could be a maxima or minima, it could be a saddle point also, because we have only checked in one direction, right? So but that's what it is, the directional derivative comes out to be 0. So your homework is to take u cap, which is u vector, which is I cap plus j cap. Let's take this, or let me take this one. Let me take this one for the next example. This. So what I am going to do is to compute the directional derivative in this direction. So let me see what it comes. So directional derivative, and let me call this as a v vector. So this will be v cap f 1 comma minus 1. So that would be, so you can similarly find that my v cap, the unit vector in the corresponding direction of v, would be just I plus j divided by root 2. Similarly what we did for u, you can easily find the unit vector, and we have gradient of my function 1 comma minus 1 dotted with the unit vector. So we already know the gradient, which is this guy. So let me plug it here. I cap minus j cap minus I cap minus j cap dotted with I plus j divided by root 2, right? So if we take the minus common and 1 by root 2 common, we have I cap plus j cap dotted with I cap plus j cap. So we have minus 1 by root 2 I dot I plus j dot j, which is actually equal to 1 plus 1 minus root 2, and therefore we have minus root 2. So my directional derivative in the direction v cap of my function at point 1 comma 1 is negative root 2. So I have given you two examples. The first example is that if I move along u cap direction, so u cap direction, I found that my directional derivative at that point was 0. What does it mean? It means that my function doesn't change at this particular point if I move in this direction, in the direction of I cap minus j cap. And similarly, I gave you another example in which I change my direction to v vector, and if I move along this direction I cap plus j cap from the same point, then my rate of change of function is actually equal to minus root 2, right? So you have this point 1 comma minus 1. If you move along one direction, your function doesn't change, but if you move along other direction, your function did change. Your directional derivative is non-zero, the function did change, right? So that's why directional derivatives are important in to figure out or to actually see the behavior of function in different directions also. So your homework would be that your function, I give you a function f of x, y, z. Let me take x square y, y square, z square plus x cube, y cube, z square, right? This is your function, and I give you a point which is 1 0 1, and I give you a vector which is I cap minus 2j cap plus 3k cap. So your task is to find the gradient at 1 0 1 and also the directional derivative along u cap. That is your homework. So please do it and post the answer in the comment section. So I will check whether you have done it correctly or not. So with that, I will end this video, and in the upcoming lectures I will do some examples on the other topic, which is gradient in spherical polar coordinates. And yeah, with that I will see you in my next video. And also, if you have not subscribed to my channel, please subscribe to my channel to show your support. And because just a single subscribe means a lot to me. It gives me a lot of encouragement to make more videos. And yeah, so please subscribe to my channel if you haven't subscribed to it. So with that, thank you, and hope to see you in my next video.